Okay, so the question that we want to answer is how to do number 8. Okay, so we need the surface area. We just started, right? We just started class, so very nice. So the surface area formula is going to be 2 times xy plus 2 times yz plus 2 times xc. You might say, well, how is that the surface area? Well, you can see that we did a practice problem just a minute ago with the volume, but now we're going to do it with the surface area. So here is xy up here, but you have 2 of them, top and bottom. This is xz up here. There's 2 of them, the front and back. And this is yz, and there's 2 of those. So we're going to do the same thing we did as we did with the practice problem. And we're going to do the derivative of surface area, or the differential. And that's going to be 2 times y plus 2 times z times dx. So I did the derivative in the x direction, and then the derivative in the y direction, and then the derivative in the z direction. And then finally, you're going to plug in x equals 95, or whatever x, y, and z you have. C is 21, and dx equals dy equals dz is this differential. And that'll give you your answer. So that wasn't too bad, was it? Okay. Actually, I can do this in my head, I'll bet, or almost. Just a minute, let me type it in. So let's see, because dx, dy, and dz are the same, this is going to be 4 times 95 plus 4 times 55 plus 4 times 21 times 0.2. Let's see if this is right. 136.8. If that's the right answer, which we didn't get it right the first time, but we're going to get it right this time. What did I say? 136.8. 136.8. Let's see. Submit. Check. Oh, good. All right. We got this? Differentials? Other issues? Questions about them? Sam doesn't like his? Or Cooper doesn't like it? Someone doesn't like it. You're going to be okay. You can do it. Oh, which error? Oh, here. I'll put it back on the screen. Here? This one? So, yeah, you put the dx, dy, dz are all the differentials. They're the error in the x, y, and z direction. And then the error in the surface area direction is just what you get when you plug in all those numbers. All right. You can do it. Yeah, the quiz is just a simple tangent plane. You're going to be thrilled. I can get the right quiz for you. We don't want this one. There it is, surface area. No, tangent. Plane. I have a misspelling. Okay, there is a typo. It did not get. It didn't get corrected by spell check. You'll see. But I'll tell you if you can't find it, I will let you know. Good job. So we're not finding the equation of the plan. It's the plane. So put an E at the end of that plan and you'll get the plane. And this is not the same. Why is this not the same? I'll put it up on the screen once I get it. There we go. if you're done, feel free to send that on over. If you're taking the entire page, you're probably not doing it right. Oh, okay. You know, you could take the entire page if you write real big.
I just want to make sure you're seeing.
Yeah, I can see it. It's beautiful. Nice, nice. That's not me. I took it. Did I have them all before I blurt out the answer? All right, so here's my answer. Curious, there it is. Hopefully it's pretty straightforward. Derivatives, plug the point into the derivatives, and then just use the form of the, I used z equals f sub x times x plus 2 minus f sub y, or plus f sub y, times y minus 1 plus z. I'm just curious, and you don't have to acknowledge if you don't want to, but I'm hoping that at least one of you did this. I will find out, of course. Nine y squared minus 5x squared, y minus 1, there. So this is wrong, but if you did that, take heart, because you won't do that on the exam. So you know, it's always fun to get it wrong in a low stakes environment like this. It looks like everyone, I don't see anyone doing that. But remember, you don't want, that's not a plane. That's the problem, is this is not a plane. Okay, let us move on. So today is, well, it's not that boring. It's sort of boring. Let's see. Let's make it at least somewhat exciting. So give me a sec. I have this. Where is it? There it is. Let's do this. Put this picture back up there really quick. There we go. I like that picture. Okay, so we have this picture here of the topographic map of the Zion National Park area. Zion National Park's huge. This is just the area in the valley with this popular hike right here. And so what I want to point out about this, or any point along a topographic map, is that where you're standing is only part of the story in terms of the slope. So, like, I mean, if I'm standing up here, it's pretty flat. Here it's very steep. That's a cliff for all intents and purposes. If you did this hike along here, this ridge, it's like a spine of rock. It's really scary. I showed you the picture so that, you know, this spine of rock here, you know, we've got a sheer cliff for all intents and purposes on either side. But where you are, so there's this spine right here, is only part of the story. You also are interested, if you want to know something about how steep the hike is, you know what? I will show you. This is an amazing, it's not only where you are, it's what direction you're pointing. So this, I should have had this image as well. And I've taken all of these photos myself at one point. These aren't my photos. So let me do this. Well, there's a famous section of this hike that goes up there. Here it is. I'll just pull up one of these images. These are all amazing. So here's this. I'll pull that up, put it up there. So this, where the hike, you're going up this, what's called Refrigerator Valley, and then you get to this part where you start having these switchbacks, and the switchbacks, they just come over and over again. You're going up and it's pretty steep. But I guess this is a good illustration that if you're standing right here at this switchback and you look this direction, it's actually surprisingly steep to go up this. But if you look this direction, you're looking at people's feet. I mean, this is directly below this. These are like little sheer cliffs here. So these people, directly above them is this. It's amazing how steep it is, this. And so it was necessary to cut this trail like that so that you could get up to the top. And that, if you're curious about where that is on the hike, that is in shadow. It's down here somewhere. So you go, this is the valley floor. Go up through that valley and get to it. So life goals, but if you do this hike, make sure that you do reserve a spot. Otherwise, they won't let you hike all the way to the top. And what's the point in going, right? If you can't go to the top.
Where is that spot?
Which? Oh, this is in Utah. So it's north of the Grand Canyon. The best way to get to it is fly into Las Vegas and drive north. And you get to St. George, Utah, I think it's called. Anyway, it's about 3 hours north of Las Vegas. That's further up here is that. So getting back to this, why do I have this here? It's so that I can say that, depending on what direction you're pointing, if you're standing on one of these hills, you might be pointing uphill, downhill, and it's not just north, south, east, west. You might be interested in going northwest or southeast. And so that's what the next topic is about. We're going to be interested in what's called directional derivatives. And so let's get this up here and find, where is it? It's coming. I've got a bunch of blank slides for some reason. Here we are, finally. Okay, so the slope in the x direction is f sub x. The slope in the y direction is f sub y. But I don't want to go in the x direction or the y direction. I'm going to go some other direction. So I'm going to draw a picture of this. So be patient. But this is going to be what's called the directional derivative. So here is me. And there's this direction. Okay, so give me a sec here. I'm going to switch back and forth. It's going to be annoying, but we'll do our best. So here's where I'm standing. This is an overhead view. So this is the y-axis, x-axis. And I'm interested in going that direction. That's going to be u. And so if there was a surface that I was standing on, maybe that surface would have these contours. Maybe this is the situation, and maybe that's downhill. I don't know. But whatever it is, like this could be 10, 9, 8. I don't know. I'm just making things up at this point. But in this case, d sub u of f is the directional derivative, the slope of a trail going in that direction. So you can see that a slope of a trail going that direction is going to be different from a slope of a trail going this direction. In fact, this direction, d sub v of f, is going to be close to 0. Notice that if I go this direction, I'm basically walking along the same direction as these contours. And so you would expect it to be pretty flat in this direction. This might be downhill. That's probably going to be flat. This will be uphill. So the direction you're going is going to depend. It's going to determine your slope. And we don't restrict ourselves to the, unless you're playing a video game where you can only go north, south, east, west, and you probably played these things. Anyway, you can go any direction you want, any angle you'd like. But anyway, getting back to the formula, which is all we really care about, right? Is this. Once you have your direction, what you're going to do is you're going to use this. Wait, did we do this already? This feels super familiar. The cosine and sine? Okay, we didn't do it. Anyway, the cosine and sine, I feel like we did something like this.
It's in my notes.
This?
Yeah. Wow. The equation is directional derivatives.
Okay, well, apparently we're doing it again.
I don't think we did anything with it.
Okay, well, we're doing it for sure now. Weird. Why would I do this early and then not remember it? Okay, that's all right.
Got some very vague notes on it.
Okay, well, here we're going to do it for real. And I know I've got U1, U2 here. Just ignore that for now. Think of this as being a vector. It doesn't matter how long it is or short it is. I don't care. All I care about is the direction it's going, and that means angles. Angles tell me direction, and so I figure out the angle in whatever way I can. I might have to use the tangent. to figure out the angle. But I get the angle, and then the cosine and sine of the angle are going to tell me this directional derivative. So let me go back here, and let's just say that this here, just a minute. So I'm going to have to switch back again. So I'm going to fudge a little bit here and say that this angle is about 30 degrees, which I know it isn't, but we're going to, well, it's close. I kind of made my horizontal not horizontal. So, but anyway, that's going to be, we're going to pretend that that's a 30-degree angle there. I know it's closer to 45. So if I wanted to find this directional derivative, what I would do is I would do the cosine of 30 degrees times f sub x plus the sine of 30 degrees times f sub y. That's it. It's as easy as that. Yes, we did do something like this. I remember feeling like I was flying because I had my arms pointing different directions. And I was like, let's go between those two. Yeah, we did something like this. Why is it that, well, we're doing it again. Okay, we'll do a practice, and then we will do, interesting. I see the practice. Why is it not showing up on the screen? Come on, practice. There it is. Okay, so I have these two vectors, and let's just do one of these problems. Let's do number 1 with these two vectors. And so give me a sec here to figure this out. I have to draw this. 1, 1. Vector u is -3/5 and +4/5. Okay, so that's going up here. And vector v is -5, -12. And f, I'm just going to do number 1, since apparently we did this at some point and never used it. Well, we're using it today, if we get to it. Maybe we can delay things so that we don't. My first class was able to get me to slow down to the point where we didn't finish, and they were thrilled because I was like, yeah, no homework. So you'll have homework, don't worry. It's easy homework. Okay, so what are we doing? We need to find the directional derivative of, let's do the first one, d sub u of f evaluated at 1, 1. So to do this, I need f sub x and f sub y. You can do this. I know you can. So I'm going to help you by doing this. One more. Come on. Multi. There it is. Max. Max, you know the derivative in the x direction, don't you?
2xy.
Very nice. In fact, this is becoming so simple that you could do it in your sleep almost. Sam, show off. Tell me what the derivative in the y direction is. Nice. 2y. Very good. Now, d sub u of f at 1, 1 is going to be the cosine of the angle. We'll get to that in a minute. Times f sub x evaluated at 1, 1 plus the sine of the angle, once again, defer for a minute, times f sub y evaluated at 1, 1. Since we need these things anyway, let's just compute them up here. Oops. You don't have to do it this way. I just find this to make it a little bit easier in terms of the amount of work that I have to do writing stuff. So let's plug 1 and 1 into these, and I get 2 for that and 3 for this. You can double check my math if you don't believe me. Slope in the x direction is 2. Slope in the y direction is 3, steeper. So 2, 3. Okay, let's get this cosine and sine business. Okay, so u. I guess that to figure out my angle, so here is the deal. Let's see. There's a couple of ways to go about this, and I'm loath to do it the hard way. So I'll do it the hard way. I'll just write it down. So the tangent of the angle is going to be y over x. That's one of the formulas we had, right? So that's one thing we could do. But another thing we could do, so that's option one. Another thing we can do is if you have a unit vector, then that unit vector will be the cosine and the sine of the angle. And then we don't even have to have the angle. We just will have the cosine and sine. So if you're given a vector like v or u like these, then use the unit vector method to find cosine and sine. If you're given an angle, then just compute the sine and cosine. So this will be a way to avoid having to, otherwise we're going to have to figure out the angle itself, and then you have to figure out sine and cosine of that angle. It's a pain in the butt. We don't want to do that. So let's just use the unit vector method. So let's take u here. U is equal to -3/5 and 4/5. Okay, how do we find a unit vector that points in the same direction as either u or v? Do you remember what to do? I'll bet you do. Lucas remembers. How do you find a unit vector? Yeah, that's right. So to find a unit vector, you do something like this. Unit vector is equal to v over the magnitude of v. Just take the magnitude, divide it, and that'll shorten it so it's just 1 unit long. So we need to find the magnitude of u. So I guess we need some help here. Cheyenne, do you know how to find magnitude of a vector?
It's going to be, I guess, x squared plus y squared.
Very nice. So we'll do this. Let's see, this will be 9/25. So I'll just use my mental calculator if you don't mind. So that was -3/5 squared and then 4/5 squared. So we got those? And that's 25/25. Oh, that's 1 already. Well, some of you probably looked at that original vector and thought, you know, that's already a unit vector, and it is. So we could divide that unit vector by 1, but we're going to get the same thing. It's already a unit vector, so we lucked out on this one. Sometimes you're happy because it's already a unit vector. So now all I have to do, so in other words, this is the cosine and sine of that angle. So when you have a unit vector, you're good. Okay, so let's do this. Cosine was -3/5 times the slope in the x direction plus 4/5 times the slope in the y direction. And what's this going to be? 6/5 is the final answer. Does that look right? It's as right as it's going to get. See if you can do the same thing, but do it for the vector v. So to do that, you're going to need to figure out the magnitude of v to get a unit vector for v, and that will tell you the sine and cosine of the angle for v. So here v, this angle is this here. We'll just make it blue to distinguish. So the blue angle, that blue theta, is the angle for v. And I realize this isn't to scale. I didn't bother because who cares? All we care is the direction. So we're going to do the same things. Magnitude, unit vector, plug and chug. See that. give you a minute to see if you can do that. I'll shuffle some papers up here. Shuffle, shuffle. All right, I think you've had enough time to either start or finish, hopefully. Cooper, what's the magnitude of V? Did you compute that?
Square root of 169.
So that would be 25, 5 squared, and 144, which is 12 squared. That's the square root of 169. Wait a minute, that's familiar. That's a perfect square, isn't it? What is square root of 169? Does anyone know?
13.
It is 13, yeah, very good. 13, okay, so we're good there. Now I need my unit vector, so my unit vector, let's see. So you're not here to help, but Rostin is. Rostin, what is the unit vector that points the same direction as -5, -12?
-5 over 13, -12 over 13.
Beautiful. So we got that. And it turns out that this is the cosine of whatever angle this vector makes, and this is the sine. So that's one of the reasons why this is useful. So we don't have to think in terms of like some nasty angle. I don't even know what angle this is, but it's probably ugly. All right, now let's put it all together. We got all this stuff here. And by the way, this stuff has not changed. That 2 and that 3, they're still the same. It hasn't changed. We haven't moved. So here we are. We're at Sarah. Sarah, can you rattle off what we got to write down here for d sub v of f of 1, 1? Beautiful. That's great. Good job. All right, nice work. So that's going to be what? -46/13? So a little bit steeper. You're going downhill. So it's kind of interesting. You're going uphill, but it's, well, 6/5. You would feel that. That's like climbing. It's not hiking. It's a pretty steep hill. And -46/13, that's worse than -3. Yeah, that is, you would look at that and you'd be like, I'm not going down that. That's a sheer cliff. Well, it would feel like it. Yeah, it's always surprising to me that roads, like driving up you go up like Glen Hill, that's like a 10% grade maybe. So that means it's a slope of 0.1, which is amazing that it feels so steep when you bike up it. Okay, enough of this. So we've had our fun with directional derivatives. They are not that hard. You'll have some on your homework. There's some pictures. Okay, we've done something like this, so we need to move on. Gradient. Gradient is the direction of maximal slope. Oh, I should have done this as a calculus problem. Whenever we think of maximum, right, we think of doing derivative, setting the derivative equal to 0, etc., etc. You can do this with the gradient. You can actually figure out what direction is the maximum slope by doing an optimization problem. But it always ends up being this. It always ends up being the direction of the two derivatives. So you do the derivative in the x direction, and that's going to be your x component of the gradient, and then do the derivative in the y direction, and that'll be the y component of your gradient. It's just so fascinating to me that that's the case. In fact, let's go back to this picture just briefly, just to see how this shakes out. I need to erase a couple of things so that I have room. Give me a minute here. Let's see, hopefully I won't erase too much. We'll get rid of all of this stuff apparently, and this stuff. Okay, I think that got rid of enough. I might as well go all the way. Okay, good enough. I guess that's too much. Okay, I did the best I could. So there's my two vectors. Remember the vector going the vector going up and to the left, that was going uphill. The vector going down and to the right or left also is downhill. I want to know the direction of maximum slope, and the direction of maximum slope is the gradient. This is the gradient. So the direction of maximum slope, written like this, upside down triangle, ends up being this vector, 2, 3. So you want to know what's the very steepest you can go? Well, it's almost the opposite of this direction that we were going. It's a little bit more this way, I guess. So this is the vector 2, 3. That's the steepest uphill possible. Now this gradient is important. The physicists and the engineers, you probably have seen this symbol or used it at some point, maybe not. But this idea of maximum slope helps us figure out what's going on. Well, we'll get to this with some applications. But imagine you have, an easy application is you have a mountain and you have a stream or water source at the top of the mountain, and there's a stream going down the mountain. It will always go in the direction of maximum negative slope. So it's always going to go down the quickest down that it can. And so that's, I guess, geological application. But there are also like heat-seeking particles, or like particles that, or take a positive ion and put it in a magnetic field. It will always go the direction that will push it the fastest away from any negative charge, that sort of thing. So depending on where the negative charge is, anyway, you have force fields, gravity fields, figure out where things are going. So there it is, and it turns out that the slope, if you do this, the slope of the function in this direction is just the magnitude of that gradient vector. We could go through and actually prove this, but once again, you'd have to do optimization for this, which isn't all that bad. And this is easy enough to do because you could figure out what the magnitude of this thing is, and that's going to give you the slope, and then from the slope, or not the slope, it'll give you the cosine and sine, and then you can use the formula for directional derivative. But it does work out to be exactly this, surprisingly. So what do we want to do? We want to do some examples. So I want the gradient of these things. And so let's do number 1 because it's related to the one that we just did on our picture here. So let's see, f, let's see, gradient, and I've got f is equal to x squared y plus y squared. Darn it. Yeah, you do it. Do the gradient. Give me a sec. And we'll do another one. Let's do the second one just for fun. Just a minute, I'll jot this down. F is cosine of xy. And then the gradient of f. Okay. This is actually super easy because the gradient is just the derivatives. So you can do the derivatives. In fact, we already did the derivatives of this one. Zechariah, what is the derivative of this function in the x direction?
2xy.
Yeah, that sounds familiar, doesn't it? And then, not here, too bad. Avin, what's the derivative of this function in the y direction? Wow, that sounds super familiar. Anyway, that is the gradient. And now if you want to know the gradient at a particular point, so the gradient of f at, say, 1, 1, you just plug 1 and 1 into this, and you get 2, 3. That's the direction of maximal slope. Let's see, let's make it interesting. At the point 1/2 pi, and then I want to know the magnitude of that gradient. All right, so we need our derivatives first. So do your derivatives. I'll give you a minute to see if you can work those out. Well, Roston, do you know the derivative of this function in the x direction?
Negative y sine of xy.
Yeah, sorry about this. So it's negative y sine of xy. If you're befuddled by his answer, just note that when you do the derivative, you're using the chain rule, so do the derivative of cosine first. Derivative of cosine is negative sine, then multiply by the derivative of xy with respect to x, which is just y. Nice work. And you're not here, but Cheyenne is. Can you do the derivative in the y direction?
Negative x sine of xy.
Wow, it's sort of symmetric, isn't it? It's kind of cool. Same deal. I won't belabor this. Now we're going to plug in x equals 1/2, y equals pi. Not here, but Sam is. Sam, what do you get when you plug x equals 1/2, y equals pi into this first bit? Did you say negative pi times sine of 1/2 pi? I think I misheard. Because this is a y, isn't it? And that's y. So does that do it? All right, we'll deal with the 1/2 pi here in just a minute, because we all know what the sine of pi over 2 is. If you don't, quick type it into your calculator. Okay, Zechariah, what do you get when you plug those numbers into the second part of this gradient? Okay, you're right. I'm going to write it though like this. I know, no. You're right. Okay, so then all of this becomes with sine of pi over 2. Sarah, you know what the sine of pi over 2, isn't it? Don't you? It's 1, yeah. Sine of pi over 2 is 1, so this will be negative pi, negative 1/2, and then we can do the magnitude. But that's the gradient. That's the direction. So you want to know, where do I have to point to go the maximum slope? I'm going to turn and I'm going to point that direction. So that's what that does for us. Final step, I want to know the magnitude of this, because the magnitude is the actual slope in that direction. So once you're pointing that direction, magnitude is going to tell you how steep this thing is. So take a minute and compute that. I'm confident you can do this. It's not going to be as pretty as my, I like this negative pi, negative 1/2 thing. Cooper, did you do the magnitude? Or you could do it on the fly, can't you?
Yeah. It's the pi squared and the negative half there.
All right, I thought I just saw Haven. Let him know when you see him that we saw him cycling by, just like on a wing and just happy-go-lucky. Okay, here we go. Let's do this. Sorry. It is always a joy when someone skips a class of mine and I see them in the cafeteria later in the day and they look all embarrassed. It's just always so much fun. Is he right out there now? I don't know. He looked like he was biking by. He went too fast. Yeah, you know, he was not looking this direction. He's like, I'm not gonna look there. I would have pointed. You know what you did, Haven. Okay. Oh no, I just erased it all. Very nice. So there it is. That's the magnitude. Okay, a couple little nuggets, little factoid. Gradient is always perpendicular to the level curve through a given point. Let's go back to Zion National Park one more time because it's so much fun. Actually, we're going to go back here a couple more times. But you want to know the direction of maximum slope? Just draw an arrow perpendicular to any one of these contours. It's always going to be perpendicular to the contour will be the direction of maximal slope. If you think about it, the contour is the direction of no slope. And so if you go perpendicular to the contour, you're going to be pointing either up or down as steep as possible. So you want to go as steep as possible, go that way. Even on these flat areas, you want to go as steep as possible. If you do, just go perpendicular to that contour. So that's one bit. Let's see another one for a function of 3 variables. You might say, how can you have a function of 3? Well, there are such things. The gradient is always perpendicular to level surfaces. And a level surface is kind of like a shell. If you can imagine a function of 3 variables, you would have different shells where maybe you could think of it as temperature. So if you had a heat source, maybe at the end of my little point here, and you would have the temperature would decrease as you get away from the heat source. It's probably not going to be exactly spherical, but the temperature you would have these shells, and each shell would be a different temperature, if you will, these little spheres or balls. And then the direction of maximal slope is always perpendicular to those surfaces, so normal to the surface. And I think that may be enough because we want to go track down Haven at this point and make fun of him that we saw him. Okay, so I think that should do it for Monday's homework. I think I fixed the homework where next Monday it's just gradients. If you see 2 homework assignments for Monday, just do the gradient one. I'll double check though before I leave. So stick around if you want to chat, and let Haven know he needs to watch the videos so that he can listen to his name spoken multiple times. I'm going to stop the video though right now. So it has been stopped.